Now that we have obtained our Hamiltonian for a Klein-Gordon field, that is for a free scalar boson, we are able to characterize what is a particle, what is a free scalar boson particle. And we will do that by looking at the energy spectrum of this Hamiltonian. And we saw that this is a harmonic oscillator, which we can more easily recognize by restoring H bar and C. So we have a sum of harmonic oscillators, one for each momentum k. And we know that each of these harmonic oscillators has a spectrum of energy which is discretized with equidistance between each state, and this distance in energy is just h bar omega. We can choose the energy of the ground state to be 0, and by analogy in the case of QFT, that means we choose the energy of the vacuum to be 0, so we get rid of this infinite constant with a delta function. And we also know that these A dagger and A are raising and lowering operators of the harmonic oscillator, and they are used to promote the system by one quantum of energy. So, for instance, from the ground state to the first excited state with a raising operator, or from an excited state to the one below with a lowering operator. So the action of A dagger of k is to create a disturbance of the field with momentum k. So if we act A dagger k on the vacuum, we get one particle state with a plane wave of momentum k. Let's measure the energy of this state by applying the Hamiltonian on it. We can swap A and A dagger using their commutator. So far, the only thing we know of our A and A dagger is that they have to obey these commutation relationships, which we introduced in order to recover the right commutator at equal time between the field and its canonical momentum conjugate. But this doesn't fix entirely A and A dagger. In order to really fix them, we need to define how they act on a specific state. So we usually choose the vacuum of the theory, and what we choose, what we impose, is that lowering operator, the A operator, acting on the vacuum gives 0. And that way, we entirely specify A and A dagger using this definition, this equation, and their commutators. Notice that there is some freedom, of course, in what we choose here, and in particular, what vacuum definition we use. Here we use the particle vacuum, the state where there is no excitation of the field, no particles at all, but it may be convenient sometimes to choose other vacuum. For instance, the ground state of a many-body system it can be a good choice. In that case, what you annihilate with the lowering operator is not a particle, but what we call a quasi-particle, and that's, for instance, how we describe the BCS theory of superfluidity in some many-body systems. But that's going too far. Let's just choose A on the particle vacuum equal to 0, and that kills clearly this term, and we are just left with a delta function, where the delta function kills the integral and changes omega k dash into omega k. So we see that the state k is an eigenstate of the Hamiltonian for the free Klein-Gordon field, and its eigenvalue is omega k, and omega k is just the energy for the disturbance of the field on mass shell. So we see that A dagger, so the action of A dagger on the vacuum is to create one quantum of energy by raising from the ground state the vacuum to the first quantum, h bar omega, and this quantum of energy corresponds to a particle, a disturbance of the field, which propagates on mass shell. So of course I can create more particles by applying other Heidegger's operator, and that way I can have a 2-particle state, a 3-particle state, a many-body particle state. And similarly, using this term, with k equal k dash, I can show that A annihilates a particle. So the action of A of k on the 1-particle state with momentum k returns the state to the vacuum. So interestingly, we came to the concept of a particle starting from the idea of a field, and we recovered the particles as excitation, quantized excitation of this field. So it sounds, the way we did it, that the fundamental object is the field and the particle are just, a consequence of quantum field theory. We could have done it exactly the other way. We could have started with particles and imposing a spectrum of energy which corresponds to what we expect for particles. So if I have, say, one particle at rest, the energy should be mc squared, and if I have n particles at rest, it should be n mc squared. So that naturally builds a spectrum like that, and which corresponds to a harmonic oscillator. And we could have done the entire reverse process, which will naturally have introduced fields as a consequence of our requirement for particles. So we can't really say if fields or if particles are really the fundamental object. We are working in an effective approach, an effective theory. It's likely that quantum field theory is not the ultimate answer to nature, and particles and fields are just concepts, intermediate concepts or tools to describe the physics around us.